Let us move on to our next topic of this lecture. We are now going to discuss beam quality and penetrability. Beam quality and penetrability. This is a very fundamental concept. We will understand exactly how our treatment beam behaves at different energies. You might be wondering what we actually mean when we use the term beam quality. In simple medical physics term, beam quality is a direct measure of the penetrating power of the X-ray beam. It tells us exactly how deep the radiation can penetrate into the patient body. It is basically used as a clinical proxy to describe the average energy of your treatment beam. Let us look at the balance scale on your screen. We often use the words quality and energy interchangeably in physics. So when we talk about the quality of the beam, we are simply talking about its total energy and its true ability to penetrate matter. A high quality beam simply means a high energy, highly penetrating beam. A low quality beam simply means low energy, weakly penetrating beam. Think about this in a very logical way. Consider treating a patient with beam that has low energy. This low energy beam has very weak penetrating power. It cannot travel very deep into the patient's tissue before being completely absorbed. Now look at the beam with high energy. It naturally has a much greater penetrability. It will easily penetrate much deeper through the human tissue to reach deep-seated tumors. This difference in energy also changes how we protect our patients and staff. Because a low energy beam is weak, it is very easy to stop. Therefore, you only need a very thin piece of material to successfully block it or reduce its intensity. On the other hand, a high energy beam becomes much harder to stop. Because it possesses this high penetrating power, you will need a significantly thicker material to safely block it. Let us quickly summarize these differences between low quality beam and high quality beam. A low quality beam has a low average energy level. Its penetrating power is extremely weak. It is rapidly absorbed in the superficial tissues, and it requires only a thin material for shielding. A high quality beam has a high average energy. It is highly penetrating. It provides deep and sustained tissue absorption, and it strictly requires significantly thicker material for safe shielding. We generally know that higher beam goes much deeper, but we cannot just guess this penetrating power in our daily clinical practice. Clinical intuition is never enough for accurate treatment planning. We cannot rely on simple visual estimations when treating cancer. We need a strict, reproducible, mathematical way to measure it accurately. This precise measurement will lead us perfectly into our next major concept. We will use a vital metric known as half value layer to accurately measure the beam quality. We simply call it HVL in our daily practice. This exact measurement forms the absolute foundation of the mathematics of attenuation. Let us prepare to look at the exact definition of HVL in our next slide. This is the strict definition of half value layer, HVL. Please read the exact definition clearly written on your screen. Do not miss any word. Half value layer is defined as the exact thickness of a specified material required to reduce the intensity of an X-ray beam to exactly half of its original value. Once again, half value layer is defined as the exact thickness of a specified material required to reduce the intensity of an X-ray beam to exactly half of its original value. Understand HVL on this diagram. The green block is the attenuating block shown in the diagram. You can assume it to be a shielding block or any matter. The incident original beam enters from the left side with exactly 100% intensity. This beam is monoenergetic. You can clearly see exactly 8 X-ray photons, all possessing this exact same energy entering this block. These ones. It then successfully passes through the exact thickness of this block. This specific physical thickness of the block is represented by the mathematical letter X. Suppose exactly 4 X-ray photons come out of the block. Remaining 4 are attenuated within the block. That means when the beam finally exits on the right side, the transmitted beam intensity is exactly 50%. I want you to pay very close attention to 2 specific words in this clinical definition. The very first important word is thickness. This is a physical thickness that we measure in millimeter or centimeter of a shielding material. We actively use this measured thickness as a direct clinical proxy to know the true penetrating power of our beam. The second very important word is intensity. Understanding what intensity actually means in this specific context is extremely crucial. It forms the absolute foundation of this topic and will directly protect you from very common exam traps. This could be a major exam trap for you. This is exactly where many students make a very common mistakes in their physics exams or viva. You can see a red lightning bolt on your left. This is energy. You can also see a group of blue dots on the right. These represents intensity of the beam. The word intensity strictly means the total number of photons in the primary beam. It absolutely does not mean the true penetrating power of the beam. When our treatment beam passes through exactly one half value layer, it simply halves the exact number of photons passing through. You can visibly see that the number of photons is reduced to exactly 50%. There were 40 photons which entered and 20 come out through this block. But it absolutely never reduces the actual energy of the X-ray beam by the 50%. I want you to always remember this rule. HVL halves the intensity, but it absolutely never halves the energy. Many beginners wrongly assume that reducing the intensity means making the individual photons weaker in energy. But the physical reality inside the patient is actually the complete opposite. We will see exactly why the average energy of the beam actually increases in this case in our next slide. Let us now carefully understand exactly why the energy of the beam is never halved. This large green block is attenuating block or a shielding block. When you place this block of a shielding material in the path of beam, it acts like a physical filter. We know that our clinical X-ray beam is never perfectly monoenergetic. It contains a complete mix of spectrum of varying photon energy. This is the incident beam carrying some low energy or weak photons and some high energy photons. These thin light colors are low energy photons and these bright red color are high energy photons. Notice exactly what happens inside that green block. The material will preferentially stop and absorb the weaker low energy photons. You can clearly see these weaker photons getting trapped inside the green material in our diagram. Because these weaker photons are physically removed from the group, the remaining transmitted photons are mostly high energy photons and hence penetrates this block. Now, please look at the baseline scale at the bottom of your screen. This simple scale perfectly shows the mathematics of this process. On the left side, you see the lower energy photons being actively removed from the beam. Imagine you have large number of any object of varying weight in a large bag and there is some average weight. If you remove some objects with lowest weight, your overall average weight will naturally goes up. Exactly similar thing happens here. Therefore, the average energy of the remaining transmitted beam actually increases. This specific physical process is clinically known as beam hardening. Beam hardening. As the treatment beam successfully passes through the patient tissue, it constantly filters out the weak radiation. The remaining beam becomes harder and much more penetrating. This is exactly why your second half value layer will always strictly need to be thicker than your first. Let us now look at what will happen if we place multiple layers of HVL blocks. These are two blocks placed in the path of a treatment beam. This is a primary treatment beam entering from the left side. This incident beam has exactly 100% intensity. It successfully passes through the first green block. We know that this first block is exactly one half value layer thick. So it will naturally reduce the beam intensity by exactly 50%. Now this transmitted beam travels forward to hit the second green block. This is exactly where many residents make a huge mistake in their dose calculation. They wrongly assume that the second block will simply remove the remaining 50%. They falsely believe that two half value layers will subtract exactly 100% of the primary beam. They think the final transmitted beam intensity will suddenly drop to absolute zero. But the physical reality inside your patient is completely different. Please look closely at this small orange wavy line safely exiting on the far right side of the second block. The radiation beam never truly reaches absolute zero. This is because beam attenuation is a continuous exponential reduction. it is absolutely not a simple linear subtraction. The second block will only remove 50% of the smaller remainder that enters it. Understanding this major difference is absolutely vital for your daily radiation shielding and safety. Let us see what actually happens mathematically inside the patient. Please look at this graph. This graph shows the true concept of exponential reduction due to multiple layers of attenuating blocks. Imagine we start our treatment with exactly 100% of our incident photons here. This is the primary incident beam entering the first shielding block. After successfully passing through the very first half value layer, the intensity safely drops to exactly 50%. Now comes the most important clinical step. The second HVL absolutely does not subtract another 50 from the total. It will simply remove half of the remaining 50%. This leaves us with exactly 25% of our original beam intensity. As the beam continues, the third HVL will again remove exactly half of that smaller remainder. This leaves us with exactly 12.5%. Finally, the fourth layer leaves us with exactly 6.25%. I want you to notice the shape of this specific downward curve. You're always taking exactly 50% out of a smaller and smaller remainder. This continuous percentage drop proves that the beam intensity mathematically never reaches true absolute zero. This is the fundamental reality of exponential beam attenuation. Here is another way to clearly visualize this exact same continuous percentage drop. Please look at the multiple layers of shielding or attenuating blocks shown on your screen. These are the 7 HVL placed in the path of incident beam. You can see the primary incident beam entering from the left at exactly 100%. As the treatment beam successfully pushes through each subsequent layer, it gets weaker and weaker. After passing through the first layer, the intensity strictly drops to 50%. After the second layer, it safely drops to 25%. After the third layer, it drops to 12.5%. After the fourth layer, it drops to 6.2%. After the fifth layer, it drops to 3.1%. After the sixth layer, it drops to 1.6%. And after the seventh layer, it drops to 0.8%. I want you to notice something extremely important thing here. The beam mathematically never reaches true absolute zero. You are always taking 50% out of a smaller and smaller remainder. It is just like a continuous endless division. This creates a continuous never-ending downward slope of beam intensity. This is the true physical reality of exponential attenuation inside your patient. The radiation simply becomes less and less intense as it travels deeper into the tissue. Understanding this endless percentage drop is absolutely vital for your daily shielding calculations. Let me give a very practical clinical example to prove this. When you create a custom shielding block out of lead or ceraband, our strict clinical goal is to protect the normal healthy tissue. To achieve adequate blocking, standard guidelines state that the beam transmission must be reduced to less than 5%. Or you can say that at least 95% of the beam intensity should be blocked by the shielding block. Let us look at the percentage drop to see exactly how much thickness we need. If we use exactly 4 half value layers, the transmission drops to 6.2%. This is still slightly above our 5% acceptable limit. But if we use exact 5 half value layer, the beam transmission drops safely to approximately 3.1%. This negligible transmission is perfectly acceptable for normal tissue protection. This is exactly why every standard shielding block you use in radiotherapy department must always be 5 HVL thick. Now, you might be looking at the 7th layer on your chart and wondering something. If exactly 7 half value layer drops the transmission to mere 0.8%, why do we just not use that? Ideally, we would absolutely love to achieve this practically zero transmission to protect our normal tissues. But there is a very big practical problem with using 7 layers of HVL in our daily clinic. If we design a lead block that is 7 layer thick, its physical thickness and weight will increase drastically. These blocks would simply be too thick and far too heavy for our radiation therapies to lift and mount safely every single day. Therefore, using exactly 5 layers gives us the perfect clinical balance between safe tissue protection and safe physical weight. Now let us look at the exact mathematics formula behind this continuous percentage drop. I know we medicos are poor at maths, but I will try to make it simple for you to understand. Look at the graph and the formula shown on your screen. This represents the fundamental physical reality of exponential beam attenuation. The mathematical equation is n equals n0 times E to the power of minus mu x. Once again, n equals n0 times E to the power of minus mu x. Let us carefully break down this complex looking equation so you truly understand it. First, look at the letter Z, N0. This strictly represents the original incident beam intensity. It is the total number of photons before they enter the shielding block. Next, look at the letter N on the left side of the equation. This represents the final transmitted beam intensity coming out after passing through the shielding block. It is the exact number of photons that have successfully passed through the block. Then we have this small letter E. It is simply the mathematical base of the natural logarithm that dictates this continuous decay. I know you didn't understand it, but it requires maths, but just take it as it is. Now look at the Greek letter mu. This is our very familiar linear attenuation coefficient. As we discussed earlier, this strictly tells us the true stopping power of the specific material. Finally, look at the letter X. This represents the thickness of the shielding material that the beam has to pass through. So this is the formula. Now please shift your focus to the yellow curve on the graph. On x-axis, you have the thickness of the shielding block. On y-axis, you have the number of photons. You can clearly see that as the thickness of the shielding block increases, the total photon number drops rapidly at first. But then the downward curve slowly starts to flatten out. Every time you add a physical thickness equal to exactly 1 HVL, the remaining photon number is strictly divided by 2. But please notice that no matter how far you go towards right of this graph, the yellow line mathematically never touches the absolute zero line. This simple equation forms the absolute foundation of shielding calculation. Now let us see exactly how we can use this formula to calculate our half value layer. I know looking at mathematical derivations can feel a little scary for many of us medicos. But please do not worry, I will try to make this little simple and more importantly, logical for you. Let us start with our main equation. N equals N0 times E to the power of minus mu x. N is the final transmitted intensity, which is the number of photons that successfully pass through this tissue or shielding material. N0 is the initial incident intensity, representing the exact original starting number of photons before they hit the material. E is the mathematical base of the natural logarithm used for exponential decay calculations. Mu is the linear attenuation coefficient which dictates the stopping power or the strict fractional rate at which the specific material removes photon. X is the initial thickness of shielding block. An X-ray beam must travel through the material. We already perfectly know the strict definition of HVL. It is the exact physical thickness of a shielding block or attenuating block where the transmitted intensity becomes exactly half of the original intensity. So to find this thickness of block, we simply substitute the transmitted intensity ratio with the fraction 1/2 on the left side of our equation. And on the right side, we safely replace the X, which is the thickness of block we need to find out. We replace it with the specific letters HVL. Now, we just need to solve this simple equation to find the value of HVL. To remove that mathematical base E from this equation, you must perform a very standard mathematical step. We simply take the natural log of both sides of equation. See, you absolutely do not need to do this complex calculation by yourself. You will require calculator. The calculator simply tells us that the natural log of 1/2 is exactly minus 0.693. On the right side, the natural log completely cancels out the letter E. This simply leaves us with exactly minus mu multiplied by HVL. We can now easily cancel out the minus sign on both sides of equation. Finally, we just move the 0.693 to the right side and bring HVL to the left to completely isolate HVL. This simple step gives us our final formula to calculate number of HVL we need. HVL now becomes equal to 0.693 divided by mu. Even if you completely hate mathematics, you must strictly memorize this final formula inside this box. This exact formula mathematically proves what we usually discussed earlier. Notice a very important relation here. HVL is strictly inversely proportional to the linear attenuation coefficient. The lower the linear attenuation coefficient, the higher will be the HVL. Think of the linear attenuation coefficient mu as a direct measure of a material's stopping power. If a shielding material has a very high linear attenuation coefficient, it means the material is extremely efficient at stopping radiation. Because this stopping power is so strong, you only need a very thin piece of that material, a small HVL, to successfully block 50% of the beam. Conversely, if the linear attenuation coefficient is low, either because the material is less dense or the X-ray beam energy is very high, the stopping power is weak. Because the stopping power is weak, you will naturally need a much thicker piece of material, a large HVL, to successfully reduce the beam's intensity by half. Therefore, as the linear attenuation coefficient increases, the required half value layer strictly decreases. Let us think about what this mathematical relationship actually means in your daily clinic. Look at these images. The solid blue block on the left side is made up of a material which has a very high linear attenuation coefficient. It is made up of a very dense material. It could be a rock or lead shielding block. That means it has a very high mu, linear attenuation coefficient. As you already know, a high mu means high linear attenuation coefficient. That means the material has a very high stopping power. Once again, a high mu means higher linear attenuation coefficient. That means the material has a very high stopping power. Because it is so strong at stopping radiation, you only need a very thin piece of this blue thin shielding block. You just need this thin slice to successfully reduce the beam intensity to exactly half. Therefore, a high attenuation coefficient strictly gives you a very low HVL. Did you understand this? Now please look at this porous sponge-like material on the right side. Can you notice this sponge-like material? This material has a very low mu and thus very low linear attenuation coefficient and thus a very low stopping power. Because it is very weak at stopping X-ray photons, the beam passes through it easily. Therefore, you will naturally need a much thicker piece of this sponge material. You must use this thicker piece to achieve that exact same 50% reduction in intensity. This clearly proves that a low attenuation coefficient strictly requires a very high HVL. Understanding this basic visual concept will make your daily shielding calculation much easier. Let us apply this important physics concept directly to human tissue now. We can use a simple seesaw balance to easily understand this. Please look closely at the high density material, for example bone, on the left side of this balance. We all know that bone is very heavy and very dense material. Because of this high density, bone has a very high linear attenuation coefficient. In our formula, this means bone has a high mu. It is excellent at safely stopping our X-ray photons. Because the bone is so strong, it strictly requires a very thin half-value layer. You only need a very small thickness of bone to successfully reduce the beam intensity to exactly half. See the small size of this high density block. Now look at the large block of soft tissue on the right side of this seesaw. Soft tissue has a much lower physical density. Therefore, it naturally has a much lower mu. Soft tissue does not stop X-ray photons very well. Because its stopping power is weak, it strictly requires a much thicker half-value layer. You must use a very thick block of soft tissue to achieve the exact same 50% reduction in intensity. This simple visual seesaw perfectly proves our mathematical formula. As the attenuation coefficient strictly increases, the HVL naturally decreases. And as the attenuation coefficient naturally decreases, the HVL strictly increases. Understanding this inverse proportional relationship is absolutely essential for your daily treatment planning. Let us take this physics concept out of the patient and into the treatment room. Think about the heavy lead or ceroband shielding blocks you use to shape your treatment beams. Lead is an incredibly dense metal with a very high atomic number. Because of this extreme density, lead has a massive linear attenuation coefficient. It possesses an enormous stopping power against our radiation beam. Because its stopping power is so strong, its half-value layer is extremely thin. You will only need a few centimeters, 5 to 7 centimeters of this heavy metal to successfully block the treatment beam and safely protect the surrounding healthy organs. If we try to use a low density material like water, plastic, sponge, wood, or even metals such as aluminium etc. to block that exact same beam, the required HVL would be massive. And using that massive block to place in the gantry head every day and changing it for every patient is very cumbersome job. You would need a shielding block that is physically too thick and dense to ever fit under the linear accelerator. This simple physics relationship is exactly why we strictly rely on dense metals such as lead or ceroband shielding block for our daily clinical shielding. Let us take a quick break from the heavy mathematics we just discussed. We are now going to talk about a very practical shielding transmission shortcut. While the complex equation of n equals n0 times e to the power of minus mu x is theoretically very important to understand, you will rarely use it on the clinical practice while planning radiotherapy. You simply do not have the time to calculate such complex natural logarithms in your head while treating patients. So please look at this simple formula. We are going to transition from that complex theoretical baseline to a very simple clinical shortcut. This shortcut is called the photon reduction factor, represented by the formula 2 to the power of HVL. This simple formula will be your absolute best friend for quick mental maths. Now, let us carefully break down this photon reduction factor cheat sheet. Please focus on the first column on the left, the theory versus the practice matrix. On the theory side, the exponential equation strictly requires a scientific calculator and complex natural logarithms. It is necessary for deep physics analysis, but it is completely impractical for mental math. But on the practice side, our 2 to the power of HVL shortcut requires only basic mental maths. It uses simple power of 2 and is perfectly designed for instant calculation for your clinical use and in exams. Now please look at the middle column, the missing link, translation engine. Earlier, we looked at visual bar charts showing a continuous halving of the beam. Then we looked at the complex natural logarithms mathematics. This shortcut is the perfect middle ground. It perfectly unites our intuitive visual halving with the complex decay formulas using simple power of 2. Such as 2 to the power of 3 equals 8. Finally, let us look at the most important part of your upcoming tests, the exam scenario visualizer on the right. In exams, you will be frequently tested on this specific concept by giving you tangible numbers just like this. Imagine you have an incident beam of exactly 8 photons entering a shielding block. When it exits, the transmitted beam has exactly 2 photons. Let us use our mental math logic breakdown to solve this without any calculator. Step 1. If the beam drops from 8 to 2, it has been reduced by a total reduction factor of 4. Step 2. We simply set our equation to 2 to the power of n equals 4. Step 3. Using simple mental math, we know that 2 squared equals 4, which strictly means n equals 2 HVL. Please memorize this visualizer. Whenever a board question gives you these tangible numbers, Instantly find the reduction factor and solve for n using simple power of the 2.